Hello everyone, today we're going to take a look at how molecules interact based on their charges or partial charges and polarity. So we're going to draw a couple molecules and take a look at their shapes and their intermolecular forces. So I've kind of got it broken down to tables so to guide me through the steps. Step one is always figure out how many valence electrons do we have. We're going to take a look at NH3, go to your periodic table. Nitrogen is in the 15th column, so it has 5 valence electrons. Hydrogen is in the first column, and we know it has 1 valence electron. Okay, so nitrogen has 5, and I've got 3 hydrogens, okay, because of that subscript, and each one has got 1 valence electron, so 5 plus 3, we have 8 valence electrons. Okay. Then we start off by drawing an atom in the middle, okay? Usually it's your lowest electronegative element, okay, but it's never hydrogen and never a halogen, because they will only ever make 1 bond. Okay? So once you've got that drawn, you take you draw 1 bond between each element and that central atom. Subtract that total of electrons you just drew from the original. Okay, I've got 3 bonds, and each bond has 2 shared electrons, right? And so I've got 2 valence electrons left, and then you draw those 2 as lone pairs somewhere. Okay? Like we said, if hydrogen only makes 1 bond, it only makes 1 bond because it'll only end with 2 valence electrons because of it only having 1 energy level. So it will never have a lone pair when it's bonded like this, okay? Then we check hydrogen has 2, hydrogen has 2, hydrogen has 2 because they all have 1 bond. Nitrogen has 1, 2, 3 bonds, 6 electrons plus that lone pair for a total of 8 electrons. Okay, so we can move on now. There are 3 atoms bonded to nitrogen here, each of those hydrogens, and then that 1 lone pair of electrons is still up there. Okay, to figure out the shape of our molecule, we have a chart to help us. So we've got 3 bonded atoms and 1 lone pair. So we've got electrons going in 4 different directions. Okay, because bonds are made up of electrons, and those lone pairs are obviously electrons. So we go, hey, I've got 4 electron dense areas or 4 directions with electrons, and I've got 1 lone pair. Just trigonal pyramidal. Okay, go ahead and put that there. Pyramidal. Okay, I don't know why it's all goofy right now. Whatever. All right, so now we're going to move down here to look at determining whether or not it's polar and what the intermolecular forces will be. So we are given a chart of electronegativities, and we can look here and see that down here, nitrogen is 3.0 and hydrogen is 2.1. Okay, we only do this once because we're looking at each individual bond. So if we do nitrogen minus hydrogen, okay, that's 1 bond, right? So nitrogen 3.0 minus 2.1, 0.9. Okay, and you can go back and see that yes, this indeed is a polar bond. What that means is nitrogen, being more electronegative, attracts those electrons more than hydrogen does, and so it will have a partially negative charge on it, where hydrogen will have a partially positive charge on it. So our bond polarity is polar. It's partial charges. That's what our little lowercase delta sign means, because unlike ionic bonds, they don't actually transfer the electrons. They're shared, just shared unequally. Okay. To determine the molecular polarity, we've got to go back up here and look at the shape. So all of these hydrogens here are partially positive, partially positive, partially positive. Okay. And then our nitrogen here is partially negative. Negative, okay? That lone electron pair makes it even more negative. And we saw that it's trigonal pyramidal, which means those hydrogens are all kind of to one side of that nitrogen, and the lone pair is above it, okay? And so if I can see this, because of our all of those being partially positive, partially positive, partially positive, partially negative, if I were to draw an imaginary line through the molecule, I can see that this side is partially negative and this side is partially positive. Okay? So it having 2 different ends, one being positive, one being negative, the molecule itself is also going to be polar. Okay? Now, normally we're going to call this interaction dipole-dipole interaction. Okay? Dipole meaning I've got a positive negative end, and so when you've got 2 molecules next to each other, positive ends will attract the negative ends and vice versa. But because the bond between nitrogen and hydrogen have a very strong dipole, because hydrogen is not very electronegative, it's a special type of dipole-dipole interaction called hydrogen bonding. Okay, bonds with HF and HO also do this. Okay, it's just a really strong dipole interaction. Okay, We can take a look at water now. Now you can go back to your periodic table and see that hydrogen still has 1 electron each, and there's 2 of those. Oxygen is in the 16th column, so it's got 6 valence electrons. So that gives us a total of 8 valence electrons. Okay. You can start to draw it, and we said hydrogen never goes in the middle because it'll only form 1 bond. Draw a bond between the middle atom and each of those. 2 electrons per bond, so that's 4, and we've got 4 left over. Electrons on there. Okay, and we're gonna put a dot there. 1, 2, 3, 4. We've used them all up. Go ahead and count. Hydrogen's got 1 bond, so 2 electrons, 2 electrons. They're good to go. Oxygen has 2 bonds and 2 sets of lone pairs, so 2, 4, 6, 8. Okay, that satisfies the octet rule, saying it's at its lowest possible energy state. It has 2 atoms bonded to it, and then we've got 2 sets of lone pairs, right? A pair is a set of dots, right? So every 2 dots is 1 lone pair. We go back over to our molecular geometry chart and see that if we've got 4 directions of electrons, our 2 bonds and our 2 lone pairs, with 2 lone pairs, it is going to be a bent molecule. Okay. We're going to go ahead and do the polarity now. Okay. Oxygen and hydrogen. Okay, oxygen's 3.5. Hydrogen's still 2.1, giving us a difference of 1.4, which we can look back and see that that is indeed polar. Okay? The oxygen is going to attract those electrons more than those hydrogens will in that bond. Okay? To determine our molecular polarity, we're going to go up here. We're going to draw our partial charges, our partial positive here, our partial negative on this end. Okay? And yes, we can see because it's bent, those hydrogens are pushed to one side because of those lone pairs of electrons. You can draw a line in the middle and see that this side's negative, this side's positive, and the molecule will indeed be polar. Okay. And again, this is the same thing as last time. Typically a dipole-dipole interaction because it's got a positive-negative end, but because that oxygen-hydrogen bond is so polar, it is very strong, and as we know by Coulomb's law, the stronger the charge, the stronger the force will be. Okay? The force holding in between hydrogen or water molecules is very strong. We're going to call that interaction hydrogen bonding. Okay. Last but not least, we've got SO3. Okay, use your periodic table. You'll see that they're both actually in the 6th column or 16th column. So they both have 6 valence electrons. So that gives us a total of 24 valence electrons. Sulfur is our lower electronegative element. So we're going to draw sulfur in the middle first. You're going to put your oxygens around it. You're going to draw a bond, okay, between each one of those. We've used up 6 valence electrons, and so we've got 18 left, 18 valence electrons. You're going to start putting dots down, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Okay, and then you can go through and count and see, get rid of that black line so I don't get too confused there. Each oxygen has 3 lone pairs for 6 electrons and 1 bond, so that gives oxygens 8. But sulfur here only has 3 bonds, okay, which gives it 6 electrons. And so we're going to move one of these lone pairs to make a double bond, okay? And so they're going to end up looking like this, okay? 1, 2, 3, 4, 5, 6, and double bonded to that last oxygen, okay? So we now have 3 atoms bonded to that middle, 0 lone pairs. You go to your chart and see that 3 areas with no lone pairs gives us a trigonal planar molecule. Okay? Trigonal planar. Then we go down here to check out our bond polarity, oxygen and sulfur. Using our chart, you're going to go down here and see that it is 3.5 minus 2.5, which will give us 1, and that tells us that that is a polar bond as well. Okay, polar minus gives us 1.0. Sorry. Okay, and so oxygen will be partially negative, sulfur partial positive. Go up here to draw our partial charge to see if the molecule will be polar. Oxygen's partially negative, partial negative, partial negative, partial positive. There's no way to split this molecule in half and say that one side's positive, one side's negative, because the outside of the entire molecule is negative. So this is actually a non-polar molecule. Even though it has polar bonds, they cancel out. And because there's no constant dipole, it's going to be London dispersion.